If you've spent any time at all in generative AI, you've probably played around with a large language model, a really fancy chatbot.
Sure.
But the real frontier, I think, the place where AI goes from just generating text and images to generating actual physics, that's where it gets really exciting.
Hmm.
We're talking about genuine physical AI, robots learning to assemble electronics or self-driving cars navigating a complex street in like a sudden hailstorm.
And that's the boundary, isn't it? That line between the digital and the physical. It's where all the biggest challenges are.
Because you can't just train them in the real world.
No, it's a disaster. I mean, it's slow, it's unbelievably expensive, and for things like autonomous driving, it's just flat out dangerous.
Right. You can't let your robot learn how to pour boiling water by, spilling it 1,000 times in your actual kitchen.
Exactly.
So, the obvious solution, the one everyone is racing towards, is to create a perfect digital twin of reality. A high-fidelity, physically consistent world simulator where failure is cheap and you can train endlessly.
And that's what we're here for today. Our mission is to really unpack a huge new paper from NVIDIA. They're introducing the next generation of their World Foundation models, or WFMs.
Built specifically for physical AI.
That's right. The models are called Cosmos Predict 2.5 and Cosmos Transfer 2.5.
And the thing that just leaped out at me from the source material was this paradox. These new models deliver way higher quality, more fidelity, more control.
Substantially higher.
But the transfer model, the Cosmos Transfer 2.5, is somehow 3.5 times smaller than the last one.
It's a massive achievement. It shows this big shift in thinking, right?
Yeah.
That the gains aren't just coming from adding more parameters. They're coming from smarter architecture and just dramatically better data.
So let's clarify what each one does.
Okay, so Cosmos Predict 2.5 is the foundational engine. It unifies text-to-world, image-to-world, and video-to-world generation all into one model.
And the other one?
And then Cosmos Transfer 2.5 is the translator, does the visual world translation. Sim-to-Real, which makes simulated graphics look real. And Real-to-Real, which augments real videos with new stuff. So, yeah, let's unpack how they built this thing.
Let's start at the very foundation, the data. Because this team seems to believe that the path to a general physical AI starts with just pure, totally uncompromised data.
The scale is immense.
Our sources say they processed over 35 million hours of raw video. That's a huge jump from the 20 million they used before.
It is, but the volume is kind of the easy part of the story. The really
Yeah.
defining thing here is the quality control. It's intense.
So from that huge pool of raw video, they derived something like 6 billion video clips.
An eye-watering number, yeah. But
Wow.
here's the kicker, the detail that shows you how committed they are to physical plausibility.
Yeah.
After this multi-stage, just ruthless filtering process, only about 200 million of those clips survived.
Hey, hold on. 6 billion clips filtered down to 200 million.
Yeah.
That's a 4% survival rate. I mean, that sounds incredibly wasteful. As someone who might use this, I have to ask, if you throw out 96% of the real world, aren't you also throwing away valuable noise, maybe some edge cases that a system needs to learn?
That's a really sharp question. And it gets right to the heart of the trade-off they're making. It's a calculated choice.
Okay.
That brutal filter is designed to just mercilessly get rid of anything that compromises physical plausibility. So things like unnatural motion, sensor noise, even like synthetic patterns from video games.
Yes, I see.
Their argument is that if your foundational data is messy, any policy you train on it will just inherit all those flaws. So they're prioritizing a pure physics-adherent data set over just broad, messy coverage.
Because the policies have to be robust to the actual laws of physics.
Exactly. And that purity, as we'll see, is what really unlocks the generalization later on.
So that reframes the filter. It's not a waste operation, it's quality assurance. Okay, so let's move from the data to the engine. The paper mentions a major architectural shift. They've moved away from diffusion models to a flow-based architecture, specifically flow matching. Why do that?
It's a move toward greater training stability and speed. Flow matching, or FM, is mathematically related to diffusion, but they differ in how they train the network.
How so?
The FM architecture uses what's called a velocity-based formulation. It's a bit in the weeds, but what it means in practice is that the model gets a much more direct, cleaner target to aim for during the training process.
Okay, so maybe we can think of it like the diffusion approach takes a lot of messy, probabilistic little steps to get to the final image.
Right.
Well, the flow-based approach is more like following a smooth, clean vector field straight to the answer.
That is a perfect analogy.
Mm-hmm.
It results in smoother optimization, which means faster training, And I mean, you can really see it, just a noticeable improvement in the quality of the videos it generates.
More temporally consistent.
Exactly. They just look and feel better.
And once the architecture was sorted, they also upgraded how the model understands instructions. They replaced the standard T5 text encoder.
Yeah, they swapped it for their own Cosmos Reason 1. It's a specialized physical AI vision language model, a VLM.
And that's key because
They don't just need a simple text label. They need a rich, deep understanding of the action and the environment. By sort of stacking activations from the VLM, they get a much richer embedding.
which allows for finer control.
Much finer-grained linguistic control. You can specify really complex actions, physics, environments with a precision that just wasn't possible before.
Makes sense. Better context, better simulation. So after all this massive foundational pre-training, they still had more to do. They start with supervised fine-tuning, or SFT.
Right, and this is where they use this cool trick they call model merging. So they'll fine-tune separate models on specific skills. One might be great at object permanence, another at, say, bimanual manipulation. And instead of just picking one, they combine the strengths of these specialized models into a single checkpoint. They use a technique called model soup.
Model soup. So instead of a whole shelf of different specialized tools, you're blending the best parts of each one into one master tool.
That's it. So the final model is both a generalist and a specialist in these key areas.
And then the final polish is reinforcement learning. Why add RL at the end?
Because SFT is really just about mimicking the data. RL, on the other hand, guided by this VLM-based reward model called Video Line, it judges the quality and the coherence of the output.
So RL is the step that checks the homework.
Absolutely. Video Line looks at text alignment, motion quality, visual quality, and the paper even has human voting results that show it works. The RL refined models were consistently preferred by people.
So they're using humans to validate that the simulated world is getting closer and closer to perfect.
They are. It's a staggering commitment to quality.
But quality for what, exactly? Let's get into the domain specialization, because this is where they really tailor the model for embodied AI.
That's right. The goal isn't just pretty videos. It's videos that follow the strict rules of real-world physics and embodiment. They focus their data curation on 5 pillars: robotics, autonomous driving, smart spaces, human dynamics, and physics.
Let's drill down into robotics. The source material shows the data came from all kinds of robots, including well-known datasets like Agibot and GR00T.
And it connects back to that linguistic control we talked about. The prompts they used weren't just simple labels. They were forced to be task-centric.
What does that mean in practice?
It means the captions have to chronologically detail explicit motion types. Was a robot's motion linear, or was it rotational? Which parts were moving? The arm, the wrist, the gripper.
Wow, so it turns a simple description like robot moves object into basically actionable physical instructions for an agent. The simulation can now reason about the difference between a smooth linear push and a slight twist of the wrist.
And those details are crucial for fine motor skills.
Okay, what about autonomous driving? Same level of rigor.
Absolutely. Tell us about that proprietary data setup they had.
Right. They collected about 3.1 million 20-second clips. But the key thing here is that they were all captured by 7 synchronized cameras on the vehicle, all at the same time.
And you can imagine the logistical nightmare of that. Getting all that perfectly calibrated and synced up.
For sure. But it creates this perfectly consistent multi-view representation of the world. And they didn't just drive around randomly.
No, the curation was very deliberate. They specifically collected clips to match a target distribution of difficult driving attributes. They were hunting for edge cases.
Exactly. It wasn't just sunny California highways. They deliberately included specific amounts of weather drive versus snow-different regions like the U.S. versus Europe.
Different traffic patterns, yeah.
Traffic density, and even uncommon road structures like tunnels or complex toll booths.
Yeah.
They're trying to build in robustness from the ground up so the model doesn't freak out the first time it sees snow.
And quickly on the physics domain, they literally created a taxonomy of physical phenomena. Shattering glass, colliding balls, fluid dynamics, all to make sure the generated videos are always plausible. They're basically trying to eliminate any visual glitch that violates inertia or gravity.
Which is the perfect lead-in to the applications. The so what of all this. This is where Cosmos Transfer 2.5 really gets to shine.
It does. But first, let's talk about a big problem in long video generation: error accumulation.
Right, when you generate a long video piece by piece, the errors start to stack up.
It's like a video game character that starts to glitch or drift after running for too long. They measure this using a score, the RNDS, which is just a formal way of tracking how quickly the simulation falls apart.
And the result here was pretty remarkable.
It really was. The new, smaller model, Cosmos Transfer 2.52b, showed far, far less reduction in that score of long sequences compared to the old one.
So less hallucination.
Significantly less hallucination and error buildup. It means you can run these world simulations for longer and they stay coherent. That's critical for training a real policy.
And I think the most compelling result in the entire paper is the robot policy learning experiment. This is the moment they prove the simulation is good enough to generate useful training data.
Okay, so let's set the scene on that one. They trained a bimanual robot on a simple pick-and-place task. Apple into a bowl.
Standard stuff. But the test was when they tried to get that policy to generalize to new adversarial visual changes.
Meaning the environment looked totally different from training. They changed the color of the apple, they added a patterned tablecloth, they changed the background, dropped in distractor objects.
All the visual noise that can completely break a simple policy.
And it did. The base policy, trained only on real-world data, failed almost completely. It succeeded just once in 30 tries. It just could not handle the visual shift.
And here it is. This is the real aha moment.
The policy that was trained with synthetic augmentations generated by Cosmos Transfer 2.52b, it proved to be exponentially more robust. It got 24 successful trials out of 30.
Wow.
In the exact same unseen scenarios. It tells you the variability generated by the world model was high fidelity enough to train a policy that could generalize. The robot learned to focus on the task and the physics, not the color of the tablecloth.
That's incredible. The performance gap was closed just by adding synthetic data from this world model. That really confirms the fidelity.
It does.
Okay, shifting to autonomous driving, the multi-view control is obviously critical there.
For driving, they built a specialized model that's conditioned on what they call a world scenario map. Think of it like a technical blueprint of the environment.
So instead of just generating video from a text prompt, they're translating a detailed map with lane lines, traffic lights, 3D locations of other cars into a photorealistic sensor stream.
Exactly. They are controlling every pixel based on a ground truth blueprint. And that map is projected onto all 7 camera views, and it's even occlusion aware.
And the fidelity gain proves it works.
It does. The generated multi-view videos got up to a 60% improvement in detection metrics, like finding 3D cuboids and lane lines, compared to the last version.
Which means the synthetic data being fed to the driving AI is just vastly more accurate and reliable.
Hugely. They also touched on using this for robotics, like mapping a humanoid's head camera view to its gripper cameras.
Which is key for manipulation, right? If your hand is blocking your main camera.
Yes. The ability to predict the view from the occluded grippers lets the agent reason about objects it can't directly see. It's all about creating a complete, coherent scene for the AI to make decisions.
So to wrap this deep dive up, we saw this massive scaling of data, but with a ruthless physics-first quality filter.
Right. Then the architectural shift to flow matching for more stability.
Then all the complex domain-specific training, the model merging, the RL polish.
And finally, the proof in the pudding. The superior real-world performance in robot generalization and driving simulation.
It's a foundational step for physical AI.
It is, and it's so important that they're releasing the models in code under the NVIDIA Open Model License. They're lowering the barrier for the whole community to build on this.
It really changes the game for how future robots and autonomous systems will learn skills. So here's the final thought for you to chew on. If AI can now reliably simulate these complex physical interactions where object colors change, where momentum and gravity are always respected, what's the next frontier of physical coherence that AI has to learn to achieve true generalized intelligence out there in the unpredictable real world?